Hello and welcome to another video in this series of tutorials where together we learn how to use Lean to write simple maths proofs. This is the fourth video in the series and we are taking things sort of slowly, taking small easy steps. And today's a slight step up actually, because we're going to see or get Lean to do a little bit of algebra for us, which we've not done before. So up to this point, we've I guess asked Lean to do things like compare numbers to see if one was bigger than another, or to see if a number was equal, a variable was equal to a number, to do substitutions and that sort of thing. Very simple, basic things, which is right. You know, we wanted to keep things simple. It's still simple today, but we're going to ask Lean to do some algebra, and hopefully it will help us with a proof. So let's dive in with the task that we've set ourselves. So here we've got an expression on the left, a plus b times a minus b. A and b are integers. Now you might recognize this as the identity for the difference of two squares. So this equals a squared minus b squared. It's kind of school level maths. You don't have to remember it. It's just a fun little thing, I guess. So what we want to do is see if we can use Lean to prove that this does equal this if a and b are integers. So not massively ambitious in terms of complexity, but just a reminder that in this course we deliberately focus on easy mathematical tasks so that we're not distracted by difficult ones, so that we can focus on learning Lean and how to use Lean to write simple proofs, so that we're ready to do more advanced or complicated things later. So as you know by now, hopefully, we try to write our maths proofs in plain English, not Lean code, just pen and paper, in a structured way, because one, is good for us in terms of structured thinking, and it also helps us prepare the logic for translation into Lean. And we've usually done that by writing out the given facts, making substitutions and so on, and justifying why we can do that. It turns out in this one there are no given facts. Let's look at the problem statement. There's no given fact. There's no something that said, you know, y equals x plus 4 or anything like that, like we had previously. We just have to prove that the left hand side is the right hand side, probably just by doing algebra. So in fact that is the answer. So if we did do this, if we got pen and paper and wrote it out, we'd multiply out the brackets, so every combination of terms is multiplied. So a times a squared there, a times minus b is this one here, minus ab, b times a is that one there, and b times minus b is minus b squared. So this is just expanding out brackets. So this equals this. And remember the structure thinking. How do we justify it? Well, for now we can say this is by algebra. And remember in the first couple of videos we talked about, well, how far down do we go in justifying things? You know, do we have to kind of talk about the properties of integers, or, you know, do we have to kind of explain, you know, what multiplying brackets means? Do we have to go all the way back to the kind of the axioms? And, you know, yes, somebody has to, but once the most common kind of results are kind of well understood and are used frequently without kind of controversy, then it's acceptable for us to have a level that we don't go below. So by algebra, this is acceptable. We don't need to kind of justify it any more deeply. So what do we do next? Well, what we can do is more algebra. We can look at this and say, well, this and this cancels out. So a times b, which is the same as b times a. Notice we've made an assumption there, haven't we? We've said a times b and b times a is the same thing. And why can we do that? Well, we can say that because a and b are given to us as integers, and we know that one of the properties of integers is that a times b is b times a, so we are using that even if we're not thinking about it. So this and this cancel out. Let me draw a picture there. So let me write that out. A plus b, a minus b equals, let's do that one first, a squared, that one, minus a times b, and I'm strictly doing it in this order, so a times b. So we've done that one. Now let's do this one, which is plus b times a, b on the left, a on the right, and then minus b squared. So our next question is cancelling out, so equals a squared minus b squared. We keep those because they're different, and we're saying that this cancels with this one, so they're not the same exactly. AB is not BA, but we know they are the same because it's a property of integers that, 3 times 2 is 2 times 3, m times n equals n times m. So that's a property of the integers, and if we didn't say these are integers, we couldn't do that assumption. So Lean is actually going to do that, check that for us, even if we don't consciously think about it. So that's minus AB plus AB. We can rewrite that by swapping those, and then we can cancel them. So being a little bit pedantic, but it's worth just being aware of what's going on. So we might do this without even thinking about it. I'm pretty much guarantee that we don't think about it, but Lean is thinking about this. Lean will look at this and say, well, BA is not the same as AB unless there's a reason they are, and the reason they are is because A and B have been defined as do we say, no, we said integers, didn't we? Yeah, integers. So that's true. Right, let's get back to what we were doing. So that actually is the conclusion that we wanted. So let's go back to the problem statement. We wanted to prove that equals that, and we've got there by algebra. So in just 2 steps. So yeah, no substitutions, no numeric comparisons, no kind of rewriting or anything like that, and we got there. So easy in some sense, but we've not done this before with Lean, so this is new. So I won't read out what I've just talked about, but if you wanted to, you could either press pause, or you could just download the slides and have a read of the explanation of that proof yourself, or go to the blog. It's worth pointing out actually that for this proof, it was basic algebra. There was just multiplying out brackets and collecting like terms. So when we say by algebra, what do we mean? Well, 2 things. We did multiplying out brackets, and we collected like terms and cancelled them. We didn't do anything else. So it's worth being clear, because that might be useful for when we write Lean code. So let's look at some Lean code. So this is some Lean code that actually implements that proof. Again, a lot of this should be familiar now, a lot of the structure of these Lean proofs. We've deliberately not written very different styles of code. You recognize all the familiar things like the comment, the importing of the maths library tactics. We've got the statement that says A and B are of a type, and here the type is integer. We've got no hypotheses, so here is where we would put the hypotheses. Remember, like H1, H2, or whatever we named them, would go after the type declarations, but we didn't do that. Well, we don't need them, so they're not there. We go straight to the overall proof objective, the goal. So here we're saying we want to prove the theorem is that a minus b times a plus b is a squared minus b squared, the difference of 2 squares. And then we're into the body of the proof. And we've said that we won't talk too much about calc for now. It's a proof by kind of simple calculation. And we'll talk more about that later when we've got something to compare it with. So, as usual, we start by writing down the thing that we want to prove something about, which is the left-hand side of that expression, a minus b times a plus b. And we say it equals something. And, we're pretty much mirroring our maths proof here. We're saying it's a squared minus ab plus ab minus b squared. And we have to justify that. Well, there's no substitution that justifies that. There's no kind of hypothesis that says, well, we can replace a with something or b with something. We need something new here. We need it's an algebraic argument that we need. In our math proof, we said by algebra, not by hypothesis 1 or given fact 2. And how do we say that in Lean? Well, we say by ring. So that tactic is what allows us to do simple algebra like multiplying out brackets. So although it sounds like an odd name, that's what we will often use to do simple algebra. As we go along, we'll learn more about why it's called ring. If you already know about mathematics and what rings are and fields are, great, you'll kind of have an insight into that. But I guess probably all I'll say now is that certain sets, like the set of integers, have properties which allows us to call them rings. If they didn't have certain properties, like if I add two numbers within any two integers, if the answer is not also within that set, then I might not be able to call it a ring. You can Google that or look it up on Wikipedia. It's not essential for now, but just to kind of give a little bit of justification for why it's called a ring. So it's kind of some of those arithmetical properties which allows Lean to be able to do the algebra. So we've expanded out the brackets. Great. We're not quite there. We've got one more step to go. And when we were looking at our maths proof, it was actually the cancelling terms. So imagine we have cancelled terms. Well, visually we can, but we want Lean to be able to justify that as well. So we say this thing equals a squared minus b squared. And to get from here to here, we, or Lean, would have had to cancel, collect like terms and cancel them. And we did that. We justified that by saying by algebra. How do we do that with Lean? Again, by algebra means by ring for now. So ring can do expanding out brackets, and ring can collect like terms and cancel them. So it's a very useful tactic, and we'll be using that quite a lot actually. It's one of those ones that will kind of be on the front of our fingertips quite a lot. So ring seems quite powerful, and we'll learn a lot more about it. But for now, we've already seen the power of ring to be able to do algebraic manipulations. So that takes us to the conclusion, which means the proof is done. Fantastic. So just to pause there and say, well, this is good. We've done something new. We've used Lean to do algebra, and that helps us prove things that we couldn't just by doing substitutions and numerical comparisons. Fantastic. There is a little bit more to say actually, so don't go away just yet. I won't read that out. That's for you to press pause and read, or download the slides. It's just the explanation of that proof. So just a comment here. The first use of that ring tactic was to justify multiplying out brackets. Let's look at that again. So this one was for multiplying out brackets. That's by ring. That's the first use of the ring tactic. The second use was to collect like terms and cancel them if possible. In our case, it cancelled minus AB and plus AB. So the ring tactic was used twice to do algebra, but slightly different algebra. And you might sort of say, well, could we combine them? Could we just have it all in one go so that we have the left-hand side equals the proof objective, the right hand side, and the whole thing is justified by algebra, by ring, and the two steps combined into one. You can do that, yeah, and you can try it. That will work. We didn't do that because I wanted us to see that ring can do those different things. It can do expanding out brackets, and it can do collecting like terms and cancelling if needed. So I just wanted to separate them out. But yeah, it can absolutely do that. In fact, let's do that live coding. So this is the Lean code in Visual Studio Code. You might prefer to use the online website. That's perfectly fine. This code can all be downloaded from the GitHub repo or totally freely available. So at the moment this is a complete proof with no errors, so there are no kind of messages from the info view telling us about any warnings or errors. That's great. And we said that we could simplify these two lines into one, and we'll delete this line. That will give us an error because there's the objective hasn't been completed. But remember, info view gives us live updates as we type, so you can usually ignore it while you're typing. And let's do this by hand. We're just going to remove those like terms. So minus AB and plus AB cancel out, and we're just left with A minus B times A plus B equals A squared minus B squared, and we can justify that by ring. And that is one line, and ring, which does algebra, has done both of those steps. And that's perfectly fine. So that was just to illustrate that you can simplify 2 or 3 lines into one, but we didn't because we wanted to illustrate that ring can do expanding out brackets and ring can do collecting like terms and cancelling. It's always useful to play with your code and kind of tweak it and see what goes wrong. It's quite educational. So what would happen if we change the type of A and B from being elements of the integers to natural numbers? Let's try it. You can see here there might be some errors, but let's try it. So we've got our proof back, and we can see that A and B are elements of Z, the symbol used for integers. Let's change that to natural numbers. Where are they? There they are. Right, so there are messages telling us Lean is not happy. I will admit Lean's error messages aren't always that helpful. It's a new language. The maths library is new as well, so hopefully over time some of them will become a little bit more kind of helpful. But for now, let's just think independently of why that might have gone wrong. Why is that? Why is it the case that if A and B, well, let's draw a picture. So we've said A plus B times A minus B equals A squared minus B squared, the standard identity for the difference two squares. And we've also said that A and B are integers. In fact, we could have also said A and B are real numbers. But as soon as we said A and B are in the set of natural numbers, which is 0, 1, 2, 3, can you see what the problem might be? Some people don't have 0, but that doesn't matter here. I shouldn't use that symbol. That's a symbol for the empty set, isn't it? Scratch that. What's the problem? Well, let's have a look at this. Adding 2, if it was natural numbers, adding 2 natural numbers is another natural number. No problem. Subtracting, there might be a problem there. So let's say A equals 5 and B equals 3. Then we've got a minus b equals 2. That's fine. Let's swap that. Let's do that the other way around. Let's say a equals 3 and b equals 5. Then we've got a minus b equals 3 minus 5. Well, we want to say it's kind of minus 2, but actually minus 2 is not in the set of natural numbers. The natural numbers are only 0, 1, 2, 3 upwards. There's no negative numbers. So that's the problem. So that's the reason Lean complained. And that's good, because the whole point of doing proofs with Lean is to validate their kind of correctness. And if it spotted something like this, an assumption we've made that's kind of, we might have overlooked, it sounds like an easy thing to not care too much about. You might have been wondering why we were obsessing about the types of the variables in the last few videos. Well, here's an example where if you get it wrong, then what you might have written with a pen and paper proof actually is not valid. You know, your results are incorrect. And this is a small example to illustrate that in a quite powerful way. I quite like this example, this counterexample, this kind of illustrative error. So Lean doesn't like that because we've said a and b are natural numbers, and then we've assumed that you can have negative natural numbers, and it can't do that. So it's caught something, which is good. That's really positive. So a and b natural numbers, and a minus b doesn't make sense if b is more than a, because natural numbers can't be negative. So that's good. So more formally, and don't worry if this next bit doesn't make sense in terms of the jargon. If you know the language, great. If not, don't worry. So Lean fails to apply the ring tactic because the set of natural numbers is not a ring under subtraction. That's fancy phrasing for simply saying that if I take two numbers from the set of natural numbers and do a subtraction, the answer is not guaranteed to be in that set. So 5 minus 3 was fine. 3 minus 5 was not fine, because 3 minus 5 is not in that set. So it's not a ring under subtraction, and that's why the ring tactic fails. So that's just a bit more formal explanation, but don't worry if that doesn't make sense yet. The main point is that Lean caught a bad assumption, which is what we want it to do. So let's go back and fix that. Go back to Z, integers, and everything is fine. Great. So let's finish with a simple exercise. And as we've said before, the idea is not to present you with kind of mathematical challenges. The idea is to keep the maths easy and just focus on practicing using Lean. So if we keep the maths easy, it's not then a kind of a double whammy in the challenge. So the challenge today is to prove another identity, which is a plus b all squared equals a squared plus b squared if we already know that ab is 0, and we know the importance now of getting the types right. So a and b are integers. That's actually not that difficult. You can do it in pen and paper quite easily. So this is a chance to practice using Lean, and you can take the code for the proof that we already have and modify it a little bit. That's the easiest thing to do, and that's still absolutely a good way of learning. This one will require using ring to do the algebra to expand that out, and it will require the rewrite tactic as well, because this then becomes a hypothesis. Let me actually write some of that down without giving you the solution, because I think this one may be presenting a challenge because we're doing two things here. So I'll just make it a bit easier for you. So we want to prove that a plus b squared equals a squared plus b squared, and we're given a fact that ab equals 0. And in terms of Lean, you know how this can then be encoded as a hypothesis, and we can call it H1 if we want to. AB equals 0, and we write that in the Lean proof. And we start with the thing that we want to prove something about, which for us is a plus b squared. And we say, well, what is that? It's something, and then we have to justify it. If we wrote the maths proof out, you'd probably, the first thing you do is expand it out. So multiplying out brackets, so a squared plus b squared plus 2ab. You probably can just say that off the top of your head. You've probably done it thousands of times in school. But we'd have to justify it. So we'd probably justify that with ring, the ring tactic, which does algebra. I won't write the code because I want you to do that. Not quite there, are we? We're almost there. This looks like that, but this is extra. We don't want that. Is there anything that can help us? Well, yes. The hypothesis says ab is 0. So we can say a squared plus b squared plus 0. Why is that? How do we justify that? By hypothesis 1. And that's a rewrite. I won't write the code. That's a substitution that gives us that. And these are things we've done in the last 2 or 3 videos. So if you need a refresher, go back. And then that's just a squared plus b squared, which is what we wanted. Your version might not include that, or it might be a slight variation, but Lean will tell you if it's not happy. So that's the idea, and you should be able to write that in code. So have fun with that. I hope you enjoyed today's video, because today we were doing something new. We were introducing the idea of doing algebra, and we'll see a lot more of that. It's very useful. See you next time. Bye.